glucose has been broken down through glycolysis, through ODP, and through the Krebs cycle. And now it's going to be turned into ADP through this process, which is the electron transport chain. So this side of the classroom represents the matrix of the mitochondria. These two rows of desks together create a phospholipid bilayer, which is the inner membrane or cristae of the mitochondria. But this is only a portion represented. This space between the desks and the counter is the intermembrane space between the cristae and the outer membrane. And so this counter is the outer membrane of the mitochondria. So now glucose has been broken down, and there's NADH and FADH, which are what are used in ETC. So this starts when NADH bumps into this end of the crustacean.
So I'm NADH, and I'm just floating around the matrix of the mitochondria. Don't have a brain, so I just happen to bump into a transport protein, and my electrons, because the protein has a higher electronegativity than me, are taken from me. This causes the protein to be reduced and me to be oxidized, and I turn into NAD plus and go back to either the Krebs cycle or the ODP.
So I am a flavoprotein. I am a transport protein on the inner membrane, and I am now reduced because I have the 2 electrons, and I'm going to take some energy for myself, and then
I take your electrons because I am more electronegative than you, and I am also a flavoprotein.
I was oxidized and he was reduced.
Yep. Ugh.
I'm a ubiquinone. I have a higher electronegative charge than the protein cluster. I'm a fat, and my job is to travel between the protein clusters and deliver the electronegative charge to the other protein cluster. I must take some energy for myself to travel back from this protein cluster.
I am cytochrome, a transport protein. I am more electronegative than ubiquinone, so I steal ubiquinone's electrons. Therefore, I'm reduced, and ubiquinone is oxidized. And
I am a flavoprotein, another transport protein. I have a higher electronegativity, so I'm going to take the electrons,
I take some energy for myself.
and I'm going to take some energy for myself and pass them on.
I'm cytochrome C. I am on the outside of the inner membrane in the intermembrane space because I'm hydrophilic. And I have a higher electronegativity than this protein, so I'm going to steal them from here and I'm going to transport them over to the iron sulfate protein. So I'm going to bring them over. And I'm going to take some energy for myself because I have to travel back. When they gave me the energy, I was reduced. And when the iron sulfate protein steals them from me, I'll be oxidized. When I go back, I burn off my energy.
We are iron sulfate protein. So now I am reduced due to the fact that I got the electrons. So I take some energy for myself.
And I take them, and I'm also another part of the iron sulfate protein, and I have the highest electronegativity out of all the transport proteins. I take energy for myself, and I am reduced because I have the electrons. And now I want to be oxidized, but I can only be oxidized by oxygen.
So I'm half O2, and I'm just like floating around in the matrix right now, and I happen to bump into the cristae, and I'm more electronegative than the protein, so I take the electrons. I take the electrons from the protein, they're low energy, and they started as high energy electrons at the beginning of the chain, but when they go through, they become low energy. And then I become O2 negative, and I attract the H+.
So we're H+ ions, and we're attracted to Mason's negative charge, and then we form water.
Yeah.
And there's that.
And we are hydrogen molecules floating around the matrix of the mitochondria. And after H2O is created, the transport proteins have collected enough energy to pump us through the inner membrane, or the cristae, into the intermembrane space. After we've been pumped through, we're all called the proton motive force!
So we're ATP synthase, and we're an enzyme embedded in the inner membrane of the mitochondria. And our job is to basically synthesize ATP, and we're both two different halves, and she works on ADP, and I work on inorganic phosphate, PI. And when the hydrogens move back into the matrix of the mitochondria, we harvest that energy and we use it to synthesize ATP.
Coming in from the Krebs cycle, I require the second protein's cluster's higher electronegativity to lose my electrons, becoming oxidized.
Now I go back to the Krebs cycle.
FADH only activated 2 clusters of protein, so that means only those 2 clusters of protein can pump through the hydrogens. Therefore, we only made 2 ATP.
So this this chart is used to gather of all of the ATP that we've made through cellular respiration. So this part is showing everything that was made in ETC. So we got 2 NADH from glycolysis. So each NADH makes 3 ATP for a total of 6 ATP from the NADHs from glycolysis. In Krebs and OTP, there's a total of 8 NADH made. Each one makes 3 ATP for a total of 24 ATP. And then we also have the 2 FADH too, each of which makes 2 ATP for a total of 4 ATP. So adding that up brings us to 34 ATP. Then we'll add this to the 4 ATP that was made as ADP through glycolysis and Krebs cycle, which made 2 ATP each, so the 4 is both of those added up. And that gives us a total of 38 ATP. But we used 2 ATP to move 2 NADHs that were made in glycolysis from the cytoplasm of the cell, which is where glycolysis occurs, into the matrix. So that's 1 ATP used for each NADH that had to be moved. So then 38 subtracting 2 leaves us with 36 ATP, which is the total amount of ATP made in cellular respiration.